Okay, so we're going to continue our discussion of the Legendre equation, but today we're going to concentrate on what are called Legendre polynomials, which are of immense use in many practical applications of this particular differential equation. Okay, so just to briefly recap, we started with what is called the Legendre equation. The equation takes this particular form. So, for example, you can note that the first two terms can be written as a single term, right? So, so d dx of something like 1 minus x square y prime, right? Because the second term is basically the derivative of can be related to the derivative of the first term. This is another way to write the Legendre differential equation usually. So we tried a series solution, noting that this series is obviously not well behaved at x equals plus minus 1, but in that interval, there is absolutely nothing wrong, and every function here is analytic. And then we plug this on sorts in, and then figure out the recursion relation. And then we found that the recursion relation is fairly straightforward, and it is related to the n that we introduced in the equation. And we later found out that if you look at these recursion relation carefully, one can of course go ahead and plug everything in and develop a series solution for y of x, which is what we did initially, right? We wrote this as a0 times a series in x and a1 times a series in another series in x. And it so happens that for this particular differential equation, the first series has only even powers of x and the second series has only odd powers, though that is not generally true. But we also noted, this is where we stopped last time, we also talked a little bit about the convergence of the series. But we also noted that last time that if this n were an integer, right, then this series actually terminates. But interestingly, not both the series terminate, only one of these series terminates. Okay, so if particularly if n is an odd integer like 3 or 5 or 7, then the odd series will terminate, because at some point you won't be able to go beyond a5 or a7 because of this n minus m term in this recursion relation. So if n turns out to be 5, then if I try to compute a7 by plugging in m equals 5, then n minus m is going to be equal to 0. So this series will only have a1, a3, and a5. It won't have an a7. So the odd series will terminate. Similarly, if n is an even number, the even series will terminate. They will not both terminate, but given a choice of n, one of them will terminate. Okay, and this leads to certain interesting possibilities. And this finite series that you get as a result of this termination is actually a polynomial in x. It's either an even polynomial or an odd polynomial, but it's some kind of a polynomial in x, and this polynomial is called the Legendre polynomial. Okay, this is where we stopped, and this is where I want to pick up the bits. Excuse me. So are there any questions about any of these things that we have talked about? Okay. So now I'm going to talk about Legendre's polynomials, and I'm not going to pay a lot of attention to whether it is gotten from an even series or an odd series. I'm going to work with the assumption that I have a set of polynomials Pn of x, right? Whether n is even or odd, I can always figure it out. So there are certain conventional choices that we will first have to get around, and we will dispose of them very quickly. These the series right here, there is you notice that there is two undetermined coefficients, right? So looking at this as an ordinary differential equation, the coefficients a0 and a1 are in my hand. Okay, so if I'm not given explicitly what the initial values are and things like that, I can fix them to whatever I want. A conventional choice of normalization or I should not actually say normalization, because we'll talk about normalization later. Choice of constant is such that Pn of x, Pn of 1 equals 1 for all n. Okay. So you usually demand that Pn of 1 is equal to 1 for all n. Now, is this absolutely necessary? Probably not. But this is the conventional choice that is employed. Okay, so the way you actually enforce this constraint is by saying that look at your series, okay, and look at the highest power of x. So remember that this is a finite series. So you look at the Legendre polynomials and fix n to some value, 57 or 35 or whatever it is that you want, and choose the highest power or the coefficient of the highest power of x. Let's call this an, and you choose this to be 2n factorial divided by 2 to the n times n factorial whole square. Okay, so once you choose the highest power this way, remember that once you choose this, the rest are determined by the recursion relation, because you have this recursion relation. Am plus 2 is blah, blah, blah. Oh, sorry, I missed this here, right? So am plus 2 is this times am. So right here, right? So now we have fixed the highest power. Okay, so we basically back calculate and work out the coefficients of the lower powers by saying that, look, my am would be something like minus of n plus 1, n plus 2 divided by n minus m, and n plus m plus 1, am plus 2, right? So pretend that am plus 2 is n, which is the highest power that you have, and then work out the lower, the coefficients of the lower powers of x by back calculating from this recursion relation. Okay, so once you do this, it is guaranteed that your Pn of 1 is 1 for every n. Okay, so the proof is rather straightforward, perhaps a little algebra heavy, but I leave it to you to look it up. So let us write down a few of these Legendre polynomials. Okay, so for n equals 0, you have P0 of x, which is 1. For n equals 1, if the series terminates at n equals to 1, you have, if the series terminates n equals 2, P2 of x would be 1/2 times 3x squared minus 1. And for n equals 3, P3 is 1/2 5x cubed minus 3x, and so on and so forth. Okay, so notice that if the series terminates at n equals 3, look at P3, then the series can at most have odd powers up till n equals 3. So that's why this has an x term and an x cubed term. If the series terminates at n equals 2, the series can at most have x to the 0 term and x squared term. That's why you have an x squared, 3x squared minus 1. Okay, so the P4 would have something like x to the 4, x squared, and x to the 0 terms, and so on and so forth. Okay. So as a practical aspect, when you look at Legendre equation, more than this particular way of writing down the series solution as an infinite series, what is actually widely employed in engineering and physics are the Legendre polynomials. They have a lot of practical applications, and I will touch upon why in this lecture briefly. Okay, but before we do that, it's very easy to see that it can become very unwieldy to work out these Legendre polynomials by looking at the series solution every time, and you don't actually need to look at the series solution every time to work out the P0, P1s, and P2s. There is actually an easier way, and we will talk a little bit about this easier way, and then we'll move on to why Legendre polynomials are actually kind of cool objects. Okay, so here's the basic idea. Suppose if you want to figure out the polynomials for free, okay, without doing a lot of work. Okay, it turns out that there is a free lunch in this case, and you can actually do this. And the idea is actually rather cool. So let us say that, you have a sequence of functions, just like this Pn of x that we have. Sequence of functions. Okay, let's call this f0 of x, f1 of x, f2 of x, and so on and so forth. Okay, so in short, fn of x. This is a sequence in x. I'm not worried about the particular form of f0 of x, f1 of x, f2 of x. They could depend on x in any which way they want. But I'm just assuming that there is a sequence of such functions that I can write down, okay, as a solution of some differential equation or whatever. Suppose if there is a convenient way to extract the functions. What do I mean? So let me again go back to the vector algebra analogy that I used, because I'm going to come back to this later in this lecture also, right? So if I write A as 3i plus 2j plus 8k, okay? So instead of looking at this as a vector, I can look at this as a sequence of numbers 3, 2, and 8. In fact, I can write this as a column vector. Okay, nothing stops me from representing an A vector as a column vector. Now, is there a convenient way in which I can extract the entries of this column vector? Yes, of course there is. That is called the dot product. If I take the dot product of A with I extract the first entry of this column vector. If I take the dot product of A with j cap, I extract the second entry. And if I take the dot product of A with k cap, I extract the third entry. Right? So there is a way to extract the numbers, assuming that this can be written as a matrix in some fashion. There is a mathematical operation that can give us this. Now, can the same be said about functions? This is not a one-to-one analogy, but I'm just trying to motivate what we are after here. Suppose if there was some kind of a series, just like I wrote A as 3i plus 4j plus 8k or whatever. So let's call this some series G. Okay. Now this series has coefficients f0s, f0 times something plus f1 times something plus f2 times something plus blah, blah, blah. Just like A vector has 3 times I cap plus 4 times j cap plus 8 times k cap, where we are after the 3s and the 4s and the 8s, right? Not necessarily the i's and the j's in the case. Suppose if I were to write some kind of a series whose coefficients are the f0s. Okay. Now, just like the dot product in the case of a vector, is there a mathematical operation that can exist that can extract these coefficients for me in an easy fashion? Okay, so that is what I want to understand. And if a compact form for such a series G can be written down, then my job is done, because I can use whatever mathematical operation that I'm going to concoct and figure out the Legendre polynomials. Okay, this is the basic idea. So I will explain this in just 1 minute in a little more detail. So assume that there is a function G, which is a function of U and X. X is, of course, the variable and U is some parameter. And I'm going to write this as a series in powers of this parameter U. N equals 0 to infinity. And I'm going to assume that the coefficients of this series are the sequence of functions that I wish to extract. So in other words, I'm basically writing down a power series in some parameter U, whose coefficients are the sequence of functions f0. The coefficient of u0, u to the 0 is f0, u to the 1 is f1, u square is f2, and so on and so forth. Okay. The question is, what does this buy me? Because I have effectively traded one infinite series for another, right? So, but you will actually see that this actually buys you quite a lot. But first, let us actually understand what kind of a mathematical operation I would do to extract the coefficients. Well, let us write this out in gory detail. This is f0 plus u f1 plus u square f2 plus blah, 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 right? Now, if I want to extract f5, for example, now you might actually guess that there is an easy way to do this. I simply have to differentiate this with respect to u 5 times. If I differentiate this with respect to u 5 times, so notice that everything that has powers less than u drop out automatically, because I cannot differentiate u times f1 5 times. So all the powers of all the powers of u less than 5 drop out. Now all the powers of u greater than 5 remain. Okay, but the power of 5 is unique because it's going to look like some constant times f5 plus something times u times f6 plus something times u square times f7 and so on and so forth, right? So if I differentiate this function with respect to u 5 times, every term in the series whose power of u is less than 5 is going to drop out, and the term in the series with u to the 5 is going to give me some constant times f5, and the term in the series with power u to the 6th is going to give me some constant times u times f6, because there is a u to the 6th. If it gets differentiated 5 times, 5 powers of u disappear, right? And now I set u to be equal to 0 because u has done the job for me. If I set u to be equal to 0, notice that every power of u basically drops out of this equation, and the only thing that remains is some constant times f5. Okay, so I basically, if I know a compact way of summing this series, and if a compact form for G exists, and if you tell me that I need to extract f5, I will simply differentiate this function 5 times and set u to be equal to 0, and I will extract f5. Okay, so in general, I can extract f to the n in this particular fashion. If I want to extract f0, I'll simply evaluate this function at u equal to 0, where I simply get f0. I don't need to do any differentiation. Okay, so this is the equivalent of the dot product that we were talking about. So this is the convenient mathematical trick that one can employ to generate the sequence of functions f0. Suppose if I can write down a series whose coefficients are the sequence of functions, then I can turn this series into some kind of a generator for the sequence of functions. And the operation that I would do is basically I will differentiate with respect to the parameter I introduced and then set the parameter to equal to 0. And this function g is said to be the generating function for Fn. Okay, because once I know G, I can generate Fn. Now, at this point, I can understand if you're still a little dazed about this entire thing, because again, this looks like you need to figure out some kind of a G. Okay, but it turns out that for Legendre polynomials, such a G can actually be written down in a very compact fashion. And I will simply write down the G for the Legendre equation, Legendre polynomials. Generating function for Pn of x, G u comma x is equal to 1 divided by square root of 1 minus 2xu plus u square. That's it. Okay. Suppose if I have a function of this form where u is some parameter, okay, then my claim is that this can be written, this can be recast as a series, okay, in powers of u whose coefficients are the Legendre polynomials. In complete analogy with our idea here. So the idea was to write down a function which can have a series representation in some parameter u whose coefficients are the functions that you want to generate. So my claim is that this G, which I've given in a very neat and compact form in this way, is basically the generator of the Legendre polynomials. Okay, so this is a tall claim and I'll have to justify it somewhat. So I will try and justify this claim. So we'll do it two ways. I'll first evaluate the first 1 or 2 terms and show that you actually do get Pn of x. So look at this G of u comma x. Okay, so this can be written as 1 minus y to the minus 1/2, where y is 2xu minus u squared. Now, since this series is perfectly okay around x is equal to 0, x is equal to 1, whatever it is, I can, u equal to 0, u equal to 1, whatever it is, I can basically expand this as a binomial series. So I'll treat this y 2xu minus u square as some kind of a small parameter, and then we'll expand this in y. So what do I get? So this is 1 plus 1/2 times y plus 1/2 factorial times n minus 1 is the next term, right? So minus half times minus half minus 1 is minus 3/2. Sorry. Minus half minus 3/2 y square. Okay. And then I don't want to work out other things because I'll do it in a slightly better fashion. So this is just a proof of concept. So what is this? This is equal to 1 plus 1/2 2xu minus u square. Okay. And what is this guy? This is minus 3/8 2xu minus u square, the whole square, plus so on and so forth. So let us turn this into a series in u and collect the coefficients of u to the 0, u to the 1, u square, and so on and so forth. Well, both this term and this term have at least one power of u. So everything that is u to the 0 is just 1. So this is 1 times u to the 0. Now let us collect the coefficients of u. Well, this term has no coefficient that is proportional to u because it is squared. So the only coefficient of u arises out of this term, right? And that coefficient is basically x. So this is x times u to the 1. Now there is two terms that can give you a u square. There is a u square here, okay, and then there is a u square here. Now remember that I should not take the fourth power and third power arising out of the second term seriously because I also have third power and fourth power in the consecutive terms on this binomial series, which I have neglected. So I should stop at second power because I'm only expanding to second order. So the coefficient of u square from the first term is minus half, and the coefficient of u square from the first term is minus 3/8 times sorry, this is plus 3/8. So plus 3/8 times 4x squared. Okay. So if you work this out, you will actually see that this is 1 times u to the 0 plus x times first power of u plus 3x squared over 2 or 3x squared minus 1, the whole thing divided by 2 times u square, and so on and so forth. And you can see the pattern emerging. G of u comma x, if you compare to the polynomials that we wrote down, p0 is 1, p1 is x, p2 is, I made a mistake here. So this is 1/2. Okay. So, and so on and so forth. So this G, at least for the first 2 or 3 terms, seems to have the right form, right? So it certainly seems to reproduce the first few Legendre polynomials. Okay. So are there any questions about this? Okay. So I need to check if this is this number is 2 or 3. I'll do that. Okay. So basically, I've shown that this can be written as p0x times u0 plus p1x u1 plus p2x u square plus so on and so forth. Okay. Now, I have certainly shown it to you for the first few terms, but how are we guaranteed that the higher order terms also reproduce the correct piece? So, for example, are we guaranteed that the coefficient of u to the 6th is p6 of x and so on and so forth? How do we know this for the infinite series? And that is a legitimate question to ask. And then I will sort of sketch how you should show this. And then, though I will not actually do the entire calculation because it is rather straightforward. Okay. Now, the way you would actually go about showing that this is truly, really the generating function for the Legendre polynomials is to start with the form of G that I just wrote down. This is 1 minus 2xu plus u squared to the minus 1/2. Okay, so this is basically this equation. Now, you can easily show using this particular form of G that this particular differential equation is satisfied by G. 1 minus x squared. G is a function of two variables, u and x. So I'll use partial differentiation and write this as d squared g over dx square minus 2x dg, excuse me, dg dx plus u d square du square of u times g equals 0. Okay. Now this I leave it to you to show using this particular form of g that we have written, show that this equation holds true. Okay. Now this is something that you can always do. I've just written some function of two variables u and x, and I've told you that this satisfies this differential equation, which you can trivially check. But the non-trivial point is to show that this g can be written as a infinite series with the coefficients being Legendre polynomials. So to do that, let us assume that g is indeed n equals 0 to infinity u to the n Pn of x. If I substitute this, which is an assumption at this point, because this is what I'm trying to check, if I substitute this over here, then I should turn this into a differential equation for Pn. And I want to see if Pn satisfies the correct differential equation. Okay. If you substitute this on source here, you would actually get, again, which this is something you can easily show, un Pn double prime of x minus 2x un Pn prime of x, because the differentiation with respect to x will give you a Pn prime of x, and then you would have a third term n times n plus 1 un Pn of x, and this is equal to 0. Okay. Now notice that this is a series in u. Okay. This is not a series in x, this is a series in u. So basically this is something multiplying u to the n equal to 0, and the only way this series can make sense is if the coefficient of un vanishes term by term in this particular series. And equating the coefficient of u to the n to be equal to 0 gives you the equation that you hopefully recognize. So I will actually write this down and then write down the, just to be very explicit, 1 minus x squared Pn double prime minus 2x Pn prime plus n plus 1 Pn, the whole thing times un equal to 0. And the only way this can be equal to 0 is if 1 minus x squared Pn double prime of x minus 2x Pn prime of x equal to 0. Okay. In other words, we have just shown that this Pn satisfies Legendre's differential equation. So it is perfectly natural to write the generating function in this particular fashion and claim that one can generate all the Legendre polynomials this way. Okay. So this is why things like these are far more useful than looking at the series and figuring out the recursion relations and then figuring out the Legendre polynomials term by term, because it is far easier to deal with a simple function and simply look at the binomial expansion of that function and extract whatever you want. Okay, so here we have shown, again, and this is also something you should show. So we have demonstrated that if I assume that this g that I've written down is written down in terms of an expansion in u with the coefficients being Legendre polynomials, it is certainly consistent because the Pn that I have here does indeed obey the Legendre's differential equation. Okay. So as a practical aspect, this is how you extract the Legendre polynomials. Are there any questions or any comments up till now? Because now I want to talk about something that might not be covered in great detail in your book, but still something that I think is very important. Okay. So this is the idea of the Legendre functions being orthogonal functions. And basis. Okay. So remember again our discussion of basis vectors a long time ago when I introduced the notion of basis, right? So we started with a very simple notion of vector algebra, and we said that suppose if you have a basis of three vectors I, j, and k, what this means is that any vector in this three-dimensional space can be written as something times I plus something times j plus something times k. Okay, and this is very easy for us to understand because this is something that we are used to, and it's a finite series, so it's easy to wrap our heads around it. But it turns out that the same thing is true even if we have infinite series or in particular functions. In other words, there are some functions that are some kind of a basis functions. Basis functions. Just like you have basis vectors or unit vectors, but basis vectors I, j, k, there are certain basis functions. And you can expand other functions in terms of these functions. Okay. And you have already seen an example of this, I'm sure, as a Fourier series. Okay. A Fourier series is basically writing some function f of x that is periodic in some interval in terms of an cosine n pi x over L plus bn sine n pi x over L. Okay. Where ans and bns are some coefficients of this series. Basically, what I'm claiming here is exactly what I'm claiming here, except that the number of components is, of course, large. Okay. So what I'm trying to tell you is that just like a vector A can be written as a sum of a linear combination of the basis vectors, a function f of x can be written as a linear combination of the basis functions. And it is not particularly difficult for you to understand cosines and sines can serve as such basis functions because you have seen Fourier series before. Okay, but it is not important, but it's not enough to just write this down. This expansion only makes sense if you have a way of telling what the coefficients are. So in this case, the way to extract the coefficients is a dot product, right? So you take the dot product of A with I and you have a way of extracting AX. The way of extracting ANs and BNs here is also through a dot product, except that the dot product is not very simple. It's an integration, but that's also a dot product. So you write down a dot product using the rules that, for example, minus pi to pi of sine nx, excuse me, sine mx dx would be equal to 0 if m equals n and pi, sorry, if m is not equal to n, and pi if m equals n. Okay, so just like I dot I is 1 and I dot j is 0, sine x and sine 2x are two basis functions. And the dot product in this case is an integration. Okay, so it's a straightforward extension of this notion to the function space. You don't need to know what this word means, but it is nice to keep it in your repertoire. Okay, so basically all I'm claiming is that these functions, cosines and sines, can also serve as basis vectors. Of course, since they are functions, we call them basis functions. In general, if you have a set of functions an, if you have a set of basis functions an, then in some interval a to b, it can be minus infinity to infinity, minus 1 to 1, what have you. It depends on what functions you're talking about. An star am of x in general should be such that it is equal to 0 if m is not equal to n, and some constant k if m equals n. Okay, Now we might worry that this constant k is not 1, but I can always normalize these functions by square root of k. So I can claim that the functions that I have are not an, but it's 1 over square root of k times an, in which case this k vanishes and you just have 1. So this is the dot product that the excuse me, that the basis functions have to obey. Another example of basis functions is e to the ix. So you also have from minus pi to pi, e to the imx star e to the inx dx star, because these are complex functions in general. If an's are real, of course, I can drop this complex conjugate and write it as an, just like I do for cosines and sines. And this is also equal to 0 if m is not equal to n, and I think 2 pi if m equals n. So I can claim that square root 1 over square root of 2 pi e to the inx are basis functions. What do I mean? I mean that I can expand any function f of x as a linear combination of e to the inx, just like I can expand any function f as a linear combination of cosine n pi x and sine n pi x. Okay. Why is all this important? It turns out that Legendre polynomials are also basis functions. There is a deep reason as to why it is true, because the fact has to do with the fact that Legendre polynomials are gotten as a solution of what is a Hermitian differential operator. But be that as it may, the point is Legendre polynomials are also basis functions. In other words, I can expand a function f of x as some linear combination of the Pn of x. But if that is true, then Legendre polynomials should also satisfy orthogonality. So if I integrate Pn and Pm, I should get 0 if n is not equal to m. Okay, but what is the interval in which I have to integrate this? Well, you note that when we started this whole series solution business for the Legendre equations, we said that this is not analytic at x equals -1 or +1. So, but within that interval, I can always pretend that these Legendre polynomials are perfectly well. So if I integrate from -1 to +1, and Legendre polynomials are a real function, so I can drop the complex conjugate here. Pm of x, Pn of x dx will be equal to 0 if m is not equal to n. Okay. Let's actually go ahead and show this for a couple of the things that we have shown. So we know that P0 is 1 and P1 is x. So -1 to 1, P0, P1 dx would be just -1 to 1 x dx, which is obviously 0. Okay, that's just an odd function. So take P1 and an even function P2, which is 3x squared minus 1 over 2. But if I multiply an odd function by an even function, I get an odd function. So you can also show that P0, P2 dx between -1 and 1 is also 0. Okay. P2 squared will not be equal to 0. Okay. So you have to normalize the Legendre functions properly so that you get rid of this constant k, and we will come to that normalization later. But first, I will tell you a few words about how to understand this relation, how to understand these guys are actually orthogonal functions. To do this, let us go back to the very beginning and start with the differential equation for Legendre functions. P L double prime minus 2x PL prime of x plus L plus 1 PL equals 0. Okay. Let me write an identical copy of this for some other m. 1 minus x squared. So before I do that, let me write this in a slightly compact notation. I can write this differential equation as ddx of 1 minus x squared PL prime of x plus L plus 1 PL of x equals 0. Okay, this is something you can trivially check. Let me write an identical copy of this equation for a different Legendre polynomial. Let us say Pm. Plus m plus 1, Pm of x equals 0. Okay. Now call this equation 1 and call this equation 2. Now multiply equation 1 by Pm and multiply equation 2 by PL and subtract. There is a method to this madness. You will actually see that when we integrate, these things will disappear very easily. So if I do that, I get Pm ddx PL prime minus PL ddx Pm prime plus LL plus 1 minus MM plus 1 PL Pm equals 0. Okay. Now it turns out that the first row can be written in the very easy form ddx of 1 minus x squared times Pm PL prime minus PL Pm prime. I will leave this as a check for you. Plus LL plus 1 minus MM plus 1 Pm PL.
How did we get the row above?
Which one?
The Pm d by dx into 1 minus x. Yeah, that expression, how did we get it?
Okay. So you have equation 1 and equation 2, right? So I multiplied equation 1. So I will write it here. Or I will just write it in symbolic form. 1 times Pm minus 2 times PL. This is the manipulation I'm doing. Okay.
Okay, so thanks.
So regardless of these manipulations, now you have a simple enough equation that is a combination of two Legendre polynomials, Pm and PL, and of course the derivatives. All of this looks complicated, but it is actually not complicated at all because now I'm going to integrate. If I integrate this function from -1 to 1, what do I get? The first term is obviously integral of a differential is basically just the function itself, right? Pm PL prime minus PL Pm prime between +1 and -1. The second term is LL plus 1 minus MM plus 1. And I'm going to assume that L is not equal to M. So this is something I should have told you in the beginning itself. L is not equal to M. If L equals M, of course, this whole thing vanishes, right? So everything becomes trivial, but I'm going to assume that L is not equal to M. And this guy gives me -1 to 1 Pm of x, PL of x dx. And this is equal to 0. What is the first term? Well, regardless of the values of Pm and PL, 1 minus x squared is always going to vanish at x equals +/-1, right? So this term vanishes. So this tells you that since L is not equal to M, if I integrate PL, Pm between -1 and 1, they satisfy an orthogonality relation. Okay. PL and Pm are orthogonal in that sense. Legendre polynomials are orthogonal functions. This class of functions, orthogonal functions, is very important in engineering and physics because they serve as basis functions and they serve to simplify many problems. For example, in practical applications, wherever there is some kind of spherical symmetry, there will always be some kind of a Legendre equation that comes up. Okay. So whether when we solve some engineering problems with some kind of a spherical symmetry, you will always contend yourself with equations of this kind. So it's very important for you to understand what these are. As a practical aspect, it's very important for you to pay attention to Legendre polynomials. Just like, you know.
How is Pm PL dash minus PL Pm dash equal to 0?
So regardless of Pm and PL dash, it is multiplied by 1 minus x squared, right? So 1 minus x squared is 0 at x is equal to +1 or -1.
Okay, so thanks.
So the first term is always 0, which means since the whole thing is equal to 0, the second term should also be 0. Okay. So I've not told you how to normalize the Legendre functions. That's just another bit of algebra, which I don't want to do. The normalization is such that you actually get -1. So what if L equals M, right? So this the whole thing that we have developed is not true for L equals M. PL of x whole square dx turns out to be 2/2L plus 1. Okay. So usually, since you want these functions to be normalized properly, you normalize the Legendre polynomials by basically multiplying them by square root of 2L plus 1 over 2. Okay. So of course, if you are only doing mathematics, you don't have to worry about this. But if you are indeed using Legendre polynomials to solve practical problems, then you have to pay attention to such normalization factors. Okay. So the point of this class was to tell you a bit about Legendre polynomials and how they are on the same footing as, for example, your Fourier series problems. What's the Fourier series? Basically, it tells you that if you have any periodic function, in that interval, I can use cosines and sines as basis functions and expand this function. This function could look like anything, like so x. It doesn't even look very periodic in some interval, but I can still expand this function as a linear combination of cosines and sines. Any given functions can be. So similarly, if you have a function f of x, you can always expand this function f of x as a linear combination of these Legendre polynomials. Okay, and this is something that that you would see in many problems in physics and engineering, and also of course mathematics. One way in which you have probably already seen this in physics is what is called multipole expansion. So suppose if you have two charges, right, or a bunch of charges, it doesn't matter. You can expand. So suppose if you are given some combination of charges in this region and you want the potential at this point P. Okay, so this point P. And assume that this point P is a very large distance from where the charges are, then the potential at this point P can be written as sum over L equals Z to R to the L PL of cosine theta. Okay. So this is called the multipole expansion. So this is, I don't know if you have seen this in PH 101, did you? Anybody? Okay. All right, so there is many instances where in physics and engineering you see these Legendre polynomials. So maybe I can include a nice tutorial problem. So an example of this, which you can look up if you're interested, is called the multipole expansion electrostatics. So if you have not seen this before, it might be useful to take a look at it, because it tells you how the Legendre polynomials can come into naturally into problems that have some kind of a symmetry. Okay, so I will stop at this point here, and the next lecture we will switch gears and I will talk about another way to look at series solutions. For example, thus far we have looked at series solutions where the powers of x that we have seen are all integer powers, right? N equals 0, n equals 1, n equals 2, and so on and so forth. But there is also the series solution can also be used in a slightly more general fashion. And this method goes by the name of Frobenius method. And we will talk a little bit about Frobenius method the next lecture. And as a practical application of this method, we'll talk about the Bessel equation. Okay, so I'll stop at this point. And if you have any questions, you can ask me.